Once a paradigmatic case emerges, theorists determine those elements of the domain for which a given model proves predictively, manipulatively, or explanatorily adequate. Criterion of adequacy are determined in part by the needs of the theorists as well as by the elements of the domain themselves. Theoretic models necessarily depict the world through a selective lens of abstraction and the specific properties of the chosen representational medium. Categories gain generality by divorcing themselves from the fine details of individual cases to unite many instances under a common type. Choice of representational medium and the inclusion or exclusion of elements in the theoretic model introduces trade-offs between complexity, power, and tractability, where a tractable model is one in which one can calculate the answers using the model fairly easily. As theorists extrapolate the paradigm from the paradigmatic case and restructure the domain around the paradigmatic case, they gain clarity regarding these features of the theoretic model. Researchers must converge upon generally acceptable norms for determining the adequacy of predictions, of retrodictions, of manipulations, and of explanations of the phenomenon within the domain. Part of the formulation of acceptable norms involves reaching rough agreement as to the appropriate representations to be included in theoretical models, aspects of the physical system that they need to or might want to incorporate into the theoretical model, operationalizations, and uses of the models that are appropriate for solving problems. I call these acceptable uses partial potential models. One example from the text that illustrates the relationship between a theoretic model and its set of partial potential models is the ideal pendulum law. The ideal pendulum law is useful for systems in which friction at the arm pivot and resistance through the medium are negligible. Other things that are important to accurate predictions using the ideal pendulum law that aren't mentioned as often is that the arm itself is assumed to be rigid and have constancy. It's assumed that there are no deviations in the bob mass, so that the bob mass can be treated as a single point, that is, an even distribution around a center point. In addition to that, of course, we saw that the angle of displacement of the bob will similarly affect the periodicity of the pendulum, that isochronism only holds for small angles of displacement. Scientists discover all of these features of the ideal pendulum law and come to formulate a set of conventions for when it is useful and when it is not useful, for the sorts of modifications that they need to introduce to the form of the law to deal with other alternative cases, other partial potential models that they would like to deal with. Another example from the text that illustrates the relationship between a theoretic model and a set of partial potential models is the ideal gas law. The ideal gas law assumes that gas molecules are point masses that engage in perfectly elastic collisions. As a result, a gas must be under fairly low pressure and at reasonably high temperature, so that the molecules are very far apart when compared to their actual volume, and they do not interact except through collisions. Likewise, the gas must be within a limited volume because, for instance, we want to make sure that there is no appreciable gravitational force gradient within the volume of the gas. So generally, a gas behaves more like an ideal gas at a higher temperature and lower pressure. The potential energy due to intermolecular forces becomes less significant compared with the particle's kinetic energy, and the size of the molecules becomes less significant compared to the empty space between them. Gases behave very non-ideally at low temperature and high pressure, since slow-moving, closely packed molecules are more likely to interact with each other. When a gas behaves very non-ideally, we can no longer use the ideal gas law. We need to switch theoretic models to, for instance, van der Waals equation. Similarly, when the temperatures of a gas become very low or very high, the gas can enter into a phase change, and that will degrade the model's predictive capacity as well. Additionally, we find that in many cases the same formal theoretic model comes to have multiple partial potential models as theorists adapt the central insight of the paradigmatic case to diverse systems that come to populate the domain. Again, the ideal pendulum law provides us with a useful example of such a case. The ideal pendulum law, if we include a frictional coefficient, will apply to weights on springs. It will apply to standard normal ideal pendulums. and it will apply to a number of atypical pendulum-like systems that engage in relatively undampened harmonic motion. In the next and last module in this lecture, we'll finish our discussion of scientific treatments of physical domains by looking at generalized solution strategies and explanatory schemas.